Okay, we are ready to start today. Hope everybody's having a good Cinco de Mayo. It looks like up here there are quite a few people that are enjoying the holiday because there's only a couple of students in the classroom up here. I can't see you all down there. It's pointed. Oh yeah, no problem. Just see the disco ball. And it's weird because the disco ball is what's in focus. Not any, like, so the projection of my screen is out of focus. Yeah. All right. Well, great. There you go. Zoom back out. Now everybody's in focus. So there are 8 of y'all. Looks like we got a fair bit. I can't count everybody, but the only thing on the agenda today, and I think everybody knew this, is the final exam review. And then if anybody has questions about labs or stuff that they're working through, we can work on those. So going through the final exam here should only take us I don't know. Last time I said a half hour, but it took a little longer than that. But I don't think it'll take much longer than that. Just so everybody is aware, I am recording this, so if people go back and record this later, is everybody aware of what time the final exam is? I didn't put that on the review. But the final exam is actually on Tuesday, even though this is a Thursday only class. So that's the final exam time that's been given by the university. So it's, I should put that, maybe I'll just, so the final exam is Tuesday. It's on the syllabus, I think. Tuesday, May, what is that? May the 10th. 2016, obviously, at 1:30 p.m. Okay, so that's what time it is. So if you show up at 1, that's okay, and I may be here, but I might not. And on the coast, is that all right? Is that an okay time for you to proctor the final?
Yeah, that's perfect.
Okay, great. So Heather will be there to proctor the final, and then she'll send the finals up. That's the way we did the midterm too, right? You were there. Okay, great. So we're all set. So that's in what, 5 days? Because it's the 5th. So 5 days, 1:30 p.m. If I remember. Well, I've been teaching here for 12 years now, and I missed one final exam. I should have had a perfect record, right? I mean, that's what should be expected, but I did. I got confused once because the final exams sometimes are different times than regular. Well, lots of times, but I was just confused. I was in my office, so it didn't take me long to get here, but it did slip my mind. So if I'm not here, somebody come get me. I think I will be though. All right. The final exam, it's going to be very similar in format to the first exam. Oh, one more thing about that. We should still have the connection in case there are questions. So unlike the midterm, we'll be dialing in. I'll be here. Heather will be there to hand out the tests to collect them. But if there's any questions about the exam as you work through it, we can ask them through the IVN system. All right. So as far as the format, the final, which I'm pretty much done writing, so I should say, is very similar in format to the first exam. It's mostly short answer, just like the last one. Yeah, so it looked like I tried to change that to present tense, didn't quite get there. There will be a couple longer questions. The final exam will have some cumulative element to it. In other words, it's not strictly speaking just about the second half of the course. I put right here, you're going to have to build and interpret small process models like you did on the last one, the bubbles and the squares, showing a simple, very similar question as to the last one. Things that you won't have to do again are detailed questions about different interpolation methods and calculating IDW by hand. Things that that we talked about, like different geostatistical methods that we talked about in the first part of the course. That's not retested, but there are some basic overlay and table operations that you'd have to understand in order to answer some of the questions. Okay, so you should know what I think if you know intersect, union, what an intersect and what a union does, and what a spatial join can do, and what a regular join can do, and then kind of like selecting out records, you should be fine with those questions. Okay. All right. Now, moving on to the second part of the course. I won't say half because it ended up being less than half of the course. It's really just the last 4 weeks, including today. So we're gonna go over the new material that we're just going to kind of, obviously we're not going to spend as much time on it because we don't have as much time, but we're going to go over that material, particularly what is shows up on the test and what's probably the most important from the lectures. Okay, so if you remember, 4 weeks ago we started talking about spatial databases. Okay, so there's gonna be part of the test that's gonna talk about spatial databases, and in lots of the first sentences for each of these chapters, I kind of like summarized the take-home message that you should understand. So here I've written, what is spatial data? I thought I proofread this. I didn't do too good of a job. What is spatial data inside of a relational database management system? Okay. Well, spatial data itself only has a few minor differences. It's still attributes tied with points, lines, and polygons. Okay. There's some minor differences, but we didn't discuss those minor differences enough that they would even be on the test. Okay. So the data itself is very similar, okay? There's a whole course where you learn a little bit more of the subtle differences between them. Some of the things I mentioned in class were things like that most spatial databases allow for mixed types, and most spatial databases allow for different versions of the same data set to exist, but those aren't on the test, okay? So basically, you should know that spatial data inside of a relational database management system is structured very, very similar to file-based data. Okay? The difference is that the ability to do operations is part of the database system rather than being separate tools that you apply to the data. Okay? So you ask the database questions in order to perform spatial analysis instead of taking your data and applying tools to your data to get outputs. It's a different way of thinking about the processing rather than a different way to think about the data. So how is it different than GIS outside of an RDMS? Outside of an RDBMS, we do things like we did most of the time we spend in this course, where we take our data, we apply tools to the data, it runs through a process, and we get a result. Inside of a relational database management system, the processing is part of the database. Okay? And the way that we actually ask the database questions is through SQL. So the second question there is, what is SQL? SQL is, of course, an acronym that stands for Structured Query Language. Structured Query Language is what it stands for. Okay, and it's a language. It's not the same as like what you normally think of as a computer programming language. Okay, it's a language for asking databases questions. So SQL is there are different variations of SQL, but it's roughly a standard for the way that you interact with a relational database management system, including a spatial relational database management system. So SQL actually will work even if your data isn't spatial, but if your data is spatial, what does it mean that your data is spatial? Every record has points, lines, and polygons, points, lines, or polygons associated with it, okay? That's what it means that your database is. So really, data inside of it, a spatial database is only spatial because it has points, lines, and polygons associated with the records. All right. So the next question here, or the next, it's a question. What is the basic structure of an SQL statement? And then I wrote behind it, you should know what each of the statement modifiers does from slide 10 in the lecture. So let me bring up slide 10 from the lecture so everybody knows what I'm talking about. We go to spatial databases, we select the spatial databases PowerPoint. Let's make sure I got the right slide number too, okay, because that would be tragic if I didn't. All right, I did get the right slide number. So here's a basic select statement. It has to have actually each of the first two statements are necessary, select and from. All the other ones are optional, and we need to know what each of these keywords does. So after select, you list the columns that you want to extract. After the from statement, you list the tables that you want to work with. A where statement limits the selection. So you might say where state name equals Mississippi. Then we're only getting those only getting those records from the database where a column named state name equals Mississippi. Okay? What happens if in my where statement I said where, whatever the name of the shape field was, let's just say it's shape, where shape intersects Mississippi? What would that do?
Selections in Mississippi.
It would limit the results to those results that intersect with the state of Mississippi. So if I had another database, like if I had a database of counties, I could, if there was a column that said state name, I could select on that column. But what if I didn't have a column that said state name and I just had another set of records that were all the states? I could say I only want to see the counties that intersect Mississippi. And the way I write that statement would be something like this. Just I already have Word open. So the way to write a statement like that is something like this. Select, and then I would say the names of the columns. I might just say county name. And you have to have a comma in between each one. County name, I'll just say population maybe. From, and then I would say from counties, and from state, where state dot name equals Mississippi. So that's an example of an SQL statement where I'm getting just those counties. Oh no, sorry, I would say county dot state name, because this would be an attribute of the county table, counties. So this is the name of the table, and this is an attribute or a column in the county table, and I'd say counties.state name equals Mississippi. Now, if I didn't have a column called state name, I could modify this statement to where I said state.shape and say what was the anyway, I forgot the name of the actual what this is saying is, I forgot the name of this actual function, intersects. It's they all begin with SA or something like that. Spatial. Anyway, that doesn't matter. That's not going to be on the test. Select county name, population from counties and state, those two tables, where I'm saying the state shape intersects the county shape. So anytime that those two intersect each other, it would select them out. Okay. All right. Actually, to make this work, I have to have one more statement in here. And state dot name equals Mississippi. You'd have to have both of those statements in there, because if you didn't, it would select everything, because every county is in a shape. I mean, every county is in a state, but if you wanted to have a state, only the states where they're in Mississippi, you could have a statement like that. All right, you won't have to write a SQL statement this complex. You'll have to write one that's a little less complex, but you'll have to interpret one that is similar to this. Okay. All right. So that's that one. Okay. Spatial joins. How are they done in SQL? And what are some of the operators discussed in class? So we already talked about intersects. And we had from the slideshow. This is what I'm talking about here. What are some of the operators we discussed in class? So that's these right here. Intersects. It's ST. It's like SA. It's not SA. ST intersects. ST contains. ST within. Touches. Crosses. And then within. That's just, we already talked about within there. Okay. That's within a D within. That's not on the test, but that is different. D within is different than within. Only these first four. Intersects, contains within, and touches, and crosses, actually, but not this one. First four slides. All right. So spatial joins, how are they done? This is a spatial join. This is a regular join. This is a spatial join. Spatial joins are done using spatial operators. Okay, geometry operations in SQL. So you should be aware that you can ask shapes for their length or for their areas in SQL. Geometry operations. You could also ask for the centroid Just different things like that. Things that you can do in as tools in ArcGIS, but you can also do them right inside of SQL. Right? So that was the section on spatial databases. Okay, geocoding and road networks. That was the next time that we met. We talked about geocoding and road networks. And this lecture wasn't like super beefy. There wasn't a whole lot of material there, but you should understand the basic data structure and method the GIS software uses to place an address at a real-world coordinate. In other words, you should understand that the data is composed of lines that represent road networks, and those lines need to at least have a from address and a to address associated with them in order to do this. So every road segment has a from and a to address that basically tells you the address range associated with that road segment, okay? And then, optionally, you can have from tos on either side of the street, okay? All right, so that's the data structure. That's the basic data structure that needs to happen. And then the method that the GIS software uses to place an address in a real-world coordinate is that first it has to match the street name with the street name that you provide, okay? So basically it selects a number of streets that match the criteria. Then, once it's selected a number, when I say streets, it might all be the same street. For example, Hardy Street out here, okay? If we want to do address geocoding, it's going to be most accurate if we have lots of line segments that have various address ranges associated with them. Usually, inside of a big city, if you remember from the lecture, it's a city block. A city block is the best unit of measure to have. And we have a separate line segment for all the little parts of Hardy Street going down Hardy Street that have their own address range associated with it. So the software first says, okay, we're talking about Hardy Street. So in its process, it selects all of the roads that match that part of the address, the Hardy Street part. Okay, somewhere along this road, Hardy Street. Now, in some places, they're like West Hardy Street and East Hardy Street. So we would only select either West or East Hardy Street, one or the other. That way, when it goes to match the address, it doesn't make a mistake. So it selects just that road, whether that road is Hardy Street, West Hardy Street, whether it's Montague or Southern, whatever it does. It selects all those little streets. Then it finds out, using the address part of the geocode, or the address part of the address, it finds out which segment it needs to select. And so it narrows it down to a single segment. And sometimes it can't always do that. There's like two segments. For example, what if you left off the west or the east? Well, it's going to select two segments. And it's going to try to figure out which one you mean and give you a percentage. Okay, but let's just say it selects a single segment. And that single segment has an address range associated with it. So finally, what it does is it interpolates along that line segment where to place the address, whether it's 80% of the way along or 20%. So if it ranges from 100 to 200 and you've given 120, it goes 20% along that line and places the dot there. And if you have left, to and from, it will place it on either one side of the street or the other, depending on whether it's an even or odd address. Okay? If you don't, it'll just place it right along the road. Okay? If you just have a to from address, it'll just place it right along the road. So that's the basic process and the basic data structure that the GIS software uses to place an address at a real world coordinate. Once you understand that, these other questions actually fall into place pretty easily, okay? So I have sources of error and uncertainty in geocoding. So if you understand that the process is basically dependent on selecting the right road and then interpolating along a road segment, you can see that there's really three places where error could jump in. First, the roads themselves need to be in the right spatial locations. If the roads are off by a certain degree of error, your geocoding locations will be off by a certain degree of error. So, you know, if the coordinates were drawn off of an aerial photograph that wasn't registered well, then your locations where your dots are put aren't going to be located well. Because in the end, that's what we're doing. We're turning an address into a spatial coordinate. So that doesn't mean that if you were to tell somebody, okay, here's how to get there. See, I put this dot on the map. I'm going to drive there. I got to turn left on Hardy Street and right on 28th, and I go down about halfway down, and there I am. Well, you can probably still get there, even if the roads have been digitized incorrectly. As long as the roads connect to the right roads, even if they're off a little bit spatially, you can still drive there. However, if you were trying to, this is a little dark, but if you were trying to launch a missile and blow up that location, it wouldn't work as well if the roads were off by 10 or 15 meters and you geocoded, you got an address and you launched your missile. That's different than somebody navigating using streets to get. It's probably a better example than that, but that's what I pulled out right now. Okay, so that's one of the sources of error, is that the street database itself isn't spatially sound. It's not. The roads aren't in their true spatial locations, even if they all connect to one another. Now, related to that is that the road database is incomplete. Okay, you've got a road that doesn't go quite as far as it should, or it doesn't connect to the road that it shouldn't. Now, those errors will make it harder for somebody to navigate to. So, but that's all related to the same one. The road network isn't accurate. It's going to cause accuracy errors in the geolocation. Okay. All right. The second one is that the second source of error is that your address ranges aren't correct. Okay. And then the third source of error is that your address ranges are very long. Okay, the longer your road segments are, it's kind of like having low spatial resolution. If your address range, for example, goes from 1,000 to 3,000 on a particular stretch of road, it's more likely that the interpolation of where that dot goes is incorrect. So even if there are no other intersecting streets, it's helpful to break a road segment up into smaller road segments and have address ranges associated with each of those. Okay. So those are the sources of uncertainty in geocoding. Really, when I said 2 and then I said 3, those are just things that popped into my head. There's not a list of those. And the second 2 that I mentioned in my head, I was having a hard time deciding whether or not those should be 2 or 1. Okay. Basically, it boils down to your address ranges being incorrect and your streets being incorrect. Those are the 2 sources of error and uncertainty in geocoding. So that's going back to this lecture right here. Now these first, 3 slides, or these 2 slides, I actually included that in the, this information is tested, I think, because we reviewed that on the next slide. So, okay. What I'm talking about here, when I say error and uncertainty, is starting with here. So geocoding is only as accurate as your reference data. That's the first type of error that I was talking about. And then the second type of error that I was talking about is this one on the slide previous to it. Rural segments, any place where you have longer segments, you're going to have more error because the segments are longer, so it relies on more interpolation. Okay. Back to this guy. Okay, sources of reference data for geocoding. We talked about Tiger line files. Tiger line files are notoriously, they're from the census, they're notoriously bad on their geolocation. However, they're not so bad on the connectivity. So if you're trying to tell somebody how to get to a location based on a road network, based on an address, and routing somebody through a network, that's not as bad as if you're actually trying to get a real world coordinate from it. It's notoriously bad. So Tiger is free from the government, but the digitization wasn't very good. Then we talked about there's a lot of commercial providers that have gone through and tried to correct Tiger census data. There's a big market for that. And then the third one is OpenStreetMap. OpenStreetMap is what they call community driven. It's kind of Wikipedia. You can go in and edit and create your own road network. You can download data from that website as well. And so it's a road network that is non-commercial and available for people to use. So those are sources for reference data for geocoding. Okay. All right. The next week, we actually talked about networks. We particularly focused on road networks. And this lecture is related to the last lecture. So really, we spent 2 weeks on different applications of road line data. We hadn't spent too much time on this course. We spent a lot of time on points and areas. Now we're focusing on lines, which are often used as networks. We focus specifically on road networks for this course. So one of the things that I wanted to point out here, and it's on the test, is that road network connectivity and routing is based on an older field of mathematics called graph theory. And we talked about that in the course. So you need to understand these concepts: edges, nodes, and weights. Those are all things that are discussed in graph theory. So edges are the lines. Nodes are the points of connection. Now, purely speaking, graph theory isn't spatial. So it doesn't really matter where lines cross if there's not a node. Okay? In fact, you can create a graph all on paper. That's not really on the test, but there's nothing spatial about it. So when you actually visualize it, it's only for your benefit of visualizing it. You can draw it in a bunch of different ways. Think about the internet. How is the internet connected? We're connected to lots of other computers. It doesn't really matter which computers are located next to each other geographically. If you were to make a graph of how people are connected on the internet, and you drew the connections between them, it wouldn't really matter that you put those that are closer in space together. You'd probably just draw the lines, okay? All right. Now, road networks are spatial. However, they're spatial only in the sense that we need to see how to get to various places. So we draw them spatially, but they're really network graphs. Okay, so edges, nodes, and weights. Weights are the values that restrict the flow through a network, okay, or increase the flow. So in graph theory, oftentimes weights are positive influences to flow. However, in road network modeling, we often use costs, and it's like the inverse of a weight. So a cost restricts the flow across an edge or across a road. All right, finally, that's what I left out, directed versus undirected. Okay, basically, a directed graph, we can have directionality associated with the flow. In other words, going from A to B can take longer than going from B to A, or can have a higher cost associated with it than for going to B to A. So in most road networks are at least partially directed. And when we started out doing this, 20 years ago, most of the basic tools for doing network modeling didn't include directionality, but quickly, whenever you go through a city, you need to have it be directed, right? There are roads that are only one direction, one-way streets. So directed versus undirected. Undirected graphs, the connection between two nodes, it has the same weight or the same cost associated with it in either direction. All right, transit costs. So we went over a few different types of costs that you could actually apply to a road network. One of probably the biggest ones is just time. The example of the network that was just time. We talked about other things that you could use as costs, like the scenic value or the actual literal cost, like how much it costs to travel that road. Distance is probably highly correlated with the actual cost, because what's the biggest factor in driving from one place to another in terms of the cost? It's probably the actual cost of the gasoline to get there. So you could use distance, length, you could use time, you could use scenery, scenic value. There are a few different things that could be costs, but to actually use them in a network, they all need to be boiled down and considered as a single cost. So every line segment has a cost associated with it. It can be a combination of several costs, but in the end, you have to have one cost associated with each line segment or each direction of each line segment. All right, how transit cost affects routes. So all you need to know there is that if I'm doing a network analysis, that the transit costs are what we're trying to minimize. So at that point, whatever the cost is, that becomes the only factor in getting from point A to point B. In other words, if it's faster, or not, I shouldn't say faster, if it costs less to go all the way up here than it does to go like this, whatever costs are, if costs are travel time, if it takes less time to do that than do that, then the computer program chooses that. It minimizes cost. Distance doesn't matter unless distance is the cost. That's how transit costs affect routes. You'll have to do a simple routing procedure. In other words, you'll have a simple network I'll say which route would the computer choose, and you'll have to find the route that has the least cost. There'll probably only be 3 options, but you need to be able to find the one with the least cost. Okay. And then looks like this is the final one here. Well, not the final one right there. Okay. Before this fit exactly on 2 pages. Oh, it's because I added some stuff. Well, I typed in some stuff. In network applications and results. So the main result is just finding a route, right? But there's lots of things you can do once you can find a route, because it's a computer program. So the awesome thing about computers is it can do the same thing over and over and over again, really, really fast. And so finding a route is a very simple problem for the computer to do. But there are other things like finding service areas. Okay, a service area is all the area that I can get to from any point on the network within a certain amount of cost. The cost is usually time, so I'll just say, as my example, I could say all the area that I could get to within 5 minutes. That's my service area. So if I'm a fire station, I can make a map of all the area that I could get to within 5 minutes of time. That's the service area for that fire station. Okay. If I'm Domino's Pizza, and I promise my customers that I can get there in a half hour or less, and I also have to factor in the time it takes to cook the pizzas, but I could come up with the area that I could serve from my Domino's Pizza using a network study. Right, I find service areas, all the areas. So if it takes me 9 minutes to make the pizzas, I could do a 21-minute service area for my restaurant, and that would be the area. So what I could do, anytime somebody called in, I could geocode their address, or the computer could automatically geocode their address. And if it was outside or on the fringe of that service area, I could tell them, we could do it, but it's not going to be in our promised 30 minutes or less. Okay, so that's finding service areas. Finding closest facility is basically saying, okay, I'm at a certain location. Which facility, maybe which public library, or which driver's license place. I don't know what you call those places where you go get driver's license. Which one's the closest? And it's really a vehicle routing problem, but it's just a multiple vehicle route. It's just basically testing the route to each location, and there's a way that the computer actually minimizes, so it doesn't have to check ridiculous answers. Okay, but it finds the closest facility. So it's finding a bunch of routes and figuring out which one is the smallest. All right, the next one is kind of interesting, at least from a research perspective. We discussed this in class, the OD, which stands for Origin Destination Cost Matrix. What that does is it finds the cost of every origin to every destination. So it gives you a table, and there are lots of applications for having a table like that, because you can use that table to make decisions on which origin and which destinations are the most excluded, or which ones are the most central. And one measure of centrality is that you are the closest to all of the other destinations, or all the destinations. Origin and destination cost measurement, that kind of falls in that. Remember, we calculated the OD cost matrix and talked about how it related to centrality. Centrality is basically a measure of how connected you are, a particular location is in a network. And one measure how connected you are is how long it takes you to get to all the other locations in the network. Yes. Centrality. Centrality is a measure of how connected you are in a network. And the OD cost matrix is basically the way you calculate that in ArcGIS. Okay, vehicle routing problem is basically very similar to finding a route, but you're now routing into multiple locations. So if I start in someplace and I want to go to these 5 locations and return to where I am, that's a vehicle routing problem. Sometimes that's referred to as the traveling salesman problem. We brought that up in the lab, in the lecture. Okay, and then location allocation is very similar to the closest facilities and the finding service areas. And actually, I don't know if there's, I don't think there is, I'm pretty sure there's not a question on location allocation because it just builds on the other ones on the test. I think that's it. Centrality, talked about that already when we did the OD cost matrix. All right. Anybody have any questions about the test, the format, the time, anything like that? No questions down on the coast? Okay. We got a few more students up here than we had at the start. I guess it was just a Cinco de Mayo. All right. So any questions on labs or anything that you're working on? You can ask them. I'll help the students up here. Heather can help the students down there, but we'll leave the connection going. So if you have a problem that Heather can't work through, then we can try to work through it through the IVN system. And other than that, I guess we're done. So. Did you still want to go through that last one? Yeah. Start calculating out by hand. Yes, there's an extra point. So this one, you actually have to do it twice. This one you're going to use all 4 points. So this one you're going to use the 3 nearest points. Yeah, so basically it's saying it's everything within that area. Okay, so B, B, and C. B, B, and C, those are the three questions. Yeah.
I have a question, and I'm probably going to get yelled at for asking this. But apparently on the syllabus, it mentions something about paper and project.
Right.
It's really close to the end of the semester, so.
Now for this class, I think the paper, the final project, let me look it up. Network analyst.
Because I don't recall it ever really being mentioned in class or talked about it.
Yeah, man, I borrowed this. I borrowed this syllabus. I thought that I'd taken this part out of here, but it does say. Okay, so for this class, the final project is only graduate students only. Has anybody been working on a final project? I'm not getting any response. Didn't hear anybody. What's that? So I've been talking to the graduate students. I didn't realize it was on the syllabus for everybody, but I've been talking to the graduate students up here. I don't have any graduate students enrolled down there, right? Yeah. So I've been talking to them about their projects individually. And yeah, there's no final project in this course for this class. Yeah, no, the paper and the final project are the same thing. Yeah. So yes. Sorry, I had thought that I'd separated that out under undergraduate, graduate, but I didn't. I see that I didn't. In most of my syllabuses, I have a separate syllabus for graduates, and not a separate syllabus, a separate grading scheme. And I guess I didn't update that. But yeah, so yeah, there's no final project paper for the undergraduates in either location. Hopefully was that okay. Is that something that you were working on? Okay. What about you, you go by JV, right? Yeah. You weren't working on that. Okay, good. Okay. Yeah, any other questions, let me know. Okay. That was the total of the weights. You got 6.111. Okay. And then you take this and divide it by each of these. That is. Okay, I get it. And then you multiply so these are your adjusted weights right here. You multiply by the original values. It's not always 100. So it's, go back to here. So basically you multiply, so these are both 0.41 because they were both the same distance. Yeah. That's these over 2. So yeah, you multiply 5, 5, 3. This will be 5. This will be 3. Actually, see how D will be 3. That's the value of that. That's 3 times that's B times 5. And then see, what you're trying to do is figure out what the value is here. The value here is 3, the value here is 5, the value there. Whereas here, the values are 100, 160. So the R is this. Yeah, so the so R is equal to yeah. So here, I think I said that in class. That should be Q. You did it right there. Yeah, you just had your messed up. So then you just need to redo it by making each of these 3, and then you'll have this. Each of these numbers 3. But that's what you're doing right now is this question. This question, you just recalculate everything. That's what the value is raised to 3/3. Okay, great. What's up? Okay. Okay. All right, so let's pull up. Let's see. So what's the meaning of your shirt, Michael?
Facts, I mean, like, taxonomy, about plants when you're growing.
You gotta get out. No windshield survey.
Yeah, well, yeah.
You gotta get out.
Plant taxonomy.
Where do you get that? Yeah, what does the front say anything? Well, up to file, go down to add data. And say add query. All right, see if you have the connection. Did you use a different computer before? So hit connections. Hit new. Go back to that sheet. So copy and paste that. Paste that. Drop down. SQL server. And let the post press SQL. Instance. Now do the same thing. All that. Yeah, so, yeah. And then database drop in. Sure. Okay. Now it'll make a connection. Yeah, so it's like, okay, now go back to the node and oh, sorry, go back to question. So, okay. Probably does. I'm going to copy that over. Now to the rename this onsite. Bring in the streets. So this says select ST union sum of the ST length of a geometry. 100. So we need to change a few things because we need to change streets to homicide. See the word streets? Change that to homicide. Okay? Delete all of this. Actually, right after the sum, the parentheses. One more. Okay. So now start getting to all the way over to right. Okay. So here, now we need to get the count. Let's see if there's a help on that. Okay. Now go back to this one. And with count. Here. Type in count, parentheses, and then about a now type space as just say CNC actually as space. It's valid. Get rid of and get rid of the second purpose. So what we're doing is if actually now, if we go and open the attribute table, what we have is a column that shows us the count of homicides by neighborhood. So this column right here. So what's the question? The paper has the lowest number, which has the largest. Yeah. I just sorted it. There's a couple. So write that as the largest. Yeah. This is on. That's on. That's in row numbers. That would probably be better. All right. Yeah. So this is that. And the lowest, just put don't scroll all, put the one choice. Okay, yeah, so think about going back to class. What SQL modifying statement will help you find that information easily? Yeah, that'd be on the PowerPoint. But there's one called order model. That's the order by a certain column. Think about it. Although it did not tell you to do that. Think we could just go here. Type space, order by space by. Let's see. Okay. Modify your statement to include only those users and okay, so yeah, I guess that's finished. So now we'll open this. That should be ordered already. Whatever is the default, I forgot, but it'll be ordered one way or the other. Ordered already. So next, basically want to modify our statement so we only have those in main. And so what we could do there is do the same thing where we properties, change query. So what was the statement? We did talk about this just a few seconds ago. The modifier that restricts is called W. Where? Type in where. And it helps us see the names. So if we go into here and remove this, these are the columns. I don't always remember the columns. That's space. It looks like it's borough and VO. You got space equals, and needs to be quotes. I forgot what it's single double quotes. Try one. They have to be, I'm pretty sure, M1 to be capitalized. Oh, look, we already have a where statement up here. But we actually need an and up there. Delete that where statement. Space and do space. So we're borough name equals. So both of these where statements apply. Type in A or B. B. So, this is my time. So now it's calculated. Now it's only going to give you what? Right, it's only going to give us the same information, but now it's only going to give us from. Yes, that's it. Now we can look this. I'll look at the attribute table. And the next question, which we could have answered before, is how many murders is one side right now? All right. So. Okay. Modifier statement to group by borough name rather than name. So right now, we'll look at our statement here. We'll say group by name. So what's that doing? So remember that we have all of the homicides, and we're putting on top. We're putting all of these geometries, and we're grouping them by the name of the neighborhood. So now, if we group by the borough name, how's that going to change it? Yeah, it's going to group it by that larger area. So let's just backspace there and type in backspace. So we're going to group by, instead of b.name, we're going to group by b.borough name. We're going to group by the borough instead of the actual. Right? And let's delete this one because we're only going to get, just man. Delete all the way to the all the way down. Okay. So now we're just saying, doing the intersect, and grouping it by, so hit validate. So we grouped it by borough name, but we didn't. Yeah, we didn't. Okay, so ST collects by the median. Under instead of ST union. ST underscore. Collect. Take up the asset. Oh, actually, just change it. Just delete the yeah, and then go back and change this. No, delete the conflict. It doesn't matter. Just do what my case is. Okay. Change, go back up there. After comma, type in B dot. Then another comma. So you need to have that field. Okay, so now they're basically, how many polygons are there? 1, 2, 3, 4, 5. So that's what it's saying polygon. You'll open up the, yeah, that's all that's on. Or, anyway, you can look at the other. Yeah, so those are the number of homicides by each. Okay, so which borough had the most homicides? Yeah, this is correct. This is Queens. All right. Okay, you don't have to write it. You want to find out. If we wanted to find out the murder rate in the borough, the data sets would have to be on hand. So, what do you want murder rate is? How's that different than just we just have murder? Right, per population. So I'm asking what other data set would have to join in? In some major population. And then that's the end of that. Yeah. Now, what's that? So X this out. So what that SQL query was kind of like doing one, like what GIS operation did we do there basically? I don't know. We removed all the common boundaries between neighborhoods based on another attribute. That, well, yeah, so technically on this one, you were supposed to use all points. You see how you could use another point there. On this one, you're just supposed to use the three closest and use the power of 3. Yeah. 3D force systems. What's that? Oh, yeah. Do you have any more Saturday classes? Saturday meetings? Well, actually, some people said about that. Yeah.
Just listening.
So is what you're working on right there, is that for nonsense stuff?
It's like hospitals and you might be able to do like rows.
Do what?
I was working online for like, I don't know. And so like almost everything was lost. Yeah.
That's
Yeah.
So what are you trying to do?
We have said that we show you how to like calculate it, which is just hard now. So I was doing like
Yeah, code in NDVI. In NDVI or?
oh no, just well, we just use hard math to do it. I don't know. We just started doing it and try it.
Yeah, so I'm pretty sure the plans, we calculated NDVI together in our camp. And that's what it looks like right here, right? So that's what, is that what you're trying to do? Okay. So these are the different band numbers. You know what Landsat is? Landsat 8. I forgot what, I forgot what they do. Yeah, I'm pretty sure we were using Landsat 7. See, Landsat 8, 4 and 5. And Landsat 7 is 3 and 4. So let's see if it looks right. So we've got this is band 4, and then 5. Have you been up to this area of the country? So look, I've been to meetings in Seattle. And then this summer though, when I go rather than minus something. Okay. And then is this okay, or do you want to save it somewhere else? It is free.
The whole girl said it was watching TV on the screen after that.
Yeah, tell me. How's your girl?
No, no.
When you say little girl, you mean the 1-year-old or 3-year-old?
No,
What's that?
I don't know which one.
Yeah, I was always wondering what the residue is.
No.
Right.
It wasn't. Yes, right.
That's your result right there. Yeah, because please be, that's identified well. See how that's low, because there's all this, it's all city, it's all built up. And then these are like parks, and they appear bright because there's lots of vegetation there. You have to move out into the outer areas.
My brother just
Which one's the,
You're right.
okay.
Yeah.
So, so here you can see something's heavily vegetated in this area, or you can see very less vegetated. I was going to say, when you probably less and less vegetation. It's interesting. You can see like how slopes that are facing certain ways have more vegetation on them. Anyway, this result is showing you the intensity of the vegetation. So the brighter it is, the more vegetation is there.
Hey, Dr. Raver,
Yeah.
I'm gonna go ahead and go. There's only a couple of students working, and they said they didn't have any questions or anything.
Okay.
Do you want me to leave the private in doing, or do you want me to cancel it?
That's fine. You can cancel it. If anybody have any questions, just let me know.
Okay. All right. Well, I'll see you on Tuesday.
All right. See you through the IDM. I'll email you the exam before then, like Monday.
Okay. All right. That's fine. I'll put it on.
Thank you.
Great. Have a good weekend. Bye.
Anything else we can do?
Well, there's so you covered classification in the class. So we did find a way. I don't know if you did it, but in Envy there was this the ability to do a maximum likelihood classifier, and found another student on that same day under that's under spatial analysis. Maximum likelihood classification. So the thing here is it's a lot like in Envy where it's, I don't know, did you actually do this in Envy at all? So the first thing that you actually have to do is have you ever created a new shapefile in ArcGIS before? So you have to create a shapefile, and then you have to like draw polygons that represent different classes. So you could you could draw a polygon here that represents urban, and a polygon here that represents forest, and then you throw that into this create signatures. And so you say which bands you want to be the signatures, and then your sample data is the data you create that shapefile for. And then the field is the name of the class. So you can have your field called whatever. So when you create your shapefile, you want a column called name or something, and then you choose that name. So that's the one that says forest or whatever. Okay, so then you do that, and then that creates a signature file. So that file gets created on disk, and then you can run maximum likelihood classifier. You feed it the same bands that you fed it into the signature file, and then you choose that signature file that you created from the create signature file. And then obviously leave everything else, the defaults, so the first, and then say okay, and it'll output a classified raster. So it'll make a raster where it'll decide which ones are forest, which ones are urban, which ones are whatever. Alternatively, there also is the unsupervised classification. You talked about that in the class too. So you could run that, and then you could create like 15, 20 classes. You could go in there and you could name them.
Yeah.
Some of them you know, I've taught this class before. When I taught it, you know, we talked about how you could basically have like 20 different classes. 5 of them might end up being forest, or like you would then, you know, examine them and classify them yourself. So either one of those are good options. Things that you could do in MD that you can also do in GHY.
Yeah.
How's Monte going? Keeping you awake? All right. Last today. Oh, yeah.
Writing some codes for SQL.
But you don't write them in Python, you write them.
Writing in SQL.
Let's see. I think it is add PostGIS. That's just adding a table itself. And that just makes a connection. That's it. So, do you have my lab pulled up anywhere? No. That's just one of the ones?
Yeah.
So control A. Yeah, create something, right? So go over back to PDIS. And I can paste that here. And it creates it right there. And then if you have so you have, well, like let's say you also have a spatial column, because right now there's no spatial column. Now I have a spatial column. I can hit load as layer. And then geometry column, and tell which one the geometry column is. Load now. And there it is. I just loaded it up. I can move that if you want. But yeah, now you can just copy and paste those examples I had in there. I'm going to go print something out downstairs real quick.